My name is Aurelian Borgels. I'm the assistant director for the facility. And today what we're going to do is go through a video guided tour of the facility. Then I'll give you a little bit of information about the facility itself, exactly what it is, what we do in that facility, and also what we test, and provide you some option to ask some questions as you go, and also at the end of the session, we'll open the floor for everyone that has any particular topic. This session is to provide some information about a Virginia Tech Stability Wind Tunnel, which is a large facility. It's a 1.8 by 1.8 meter wind tunnel, 6 foot by 6 foot wind tunnel, and behind me you can see the fan that's powering all this. And the first thing we're going to do is go through a video guided tour of the facility, and then I'll provide you a few images of things inside the facility, different features of the facility, as well as what we do for testing. So let's start with the video.
Hi, my name is Danny Fritsch. I'm a third-year PhD candidate, and I'd like to welcome you now to the Stability Wind Tunnel. So this is the largest wind tunnel we have here at Virginia Tech, and it's one of the largest university-owned wind tunnels in the United States. We're going to take you into the test section in a little bit, but you'll see this is a very large wind tunnel. It's big enough that you can stand up inside the test section. And we do both academic research as well as a lot of industry research here. So right now we're standing in the control room. This is where the engineers sit while they're doing their wind tunnel experiments. Right here next to me, this is the control box, and this is where you can control the speed of the wind tunnel by driving the fan. And over here you can see behind me and to the side there's an array of screens. And what we can do while we're in here is we can monitor everything going on in the wind tunnel, the speed of the flow, the temperature and density, as well as some stats on what's going on with the motor and the drive, just in case there's problems, as well as all of our data acquisition systems and monitoring of what's going on in the test section. So next up, I'm going to take you into the tunnel itself. And in order to do that, we have to walk through this airlock here. And as you can see, these have some really big doors on them. And the reason we need the airlock, this tunnel will run up to about 200 miles an hour. And when it does that, the ambient pressure in the actual tunnel section will drop. So we have this airlock here to separate the engineers from the wind tunnel when that pressure drops. It's not dangerous, but it's pretty uncomfortable. So now we're in the main tunnel area. You can see the test section is that silver part that's above and behind me. So you can see this is a really big facility, and it actually extends out of the building right over here in front of me and then back behind us. This is a really big facility, and it actually did not start here at Virginia Tech. It was donated to us by NASA in the 1950s, then shipped it here down the highway and put it back together piece by piece. And since then, we've done a lot of modernization to the tunnel to get it ready for research in the 21st century. One of the biggest things we've done is this is the first ever hybrid anechoic wind tunnel. So what that means is you see behind me, this is the wall of the test section, and right now it's in what we might call its traditional or its aerodynamic configuration. But we can actually pull that wall out and replace it with one made entirely of Kevlar. And what's cool about the Kevlar is that it presents a solid barrier to the flow. So aerodynamically it acts like a normal wind tunnel, but it presents almost no barrier to sound. And then what we can do is we can back up these really large chambers right here. We call these the anechoic chambers. And you can see it's basically a really big box filled with acoustic foam. And we back that up right up against the tunnel, and we can put all kinds of acoustics instrumentation in there to measure the sound of flows going on in the wind tunnel. And that makes this facility really popular with a lot of industry partners like GE, who come here to do aeroacoustic testing for things like wind turbine blades and aircraft landings. So now we're going to go ahead and take you up into the test section and talk about some of the capabilities of the tunnel. Alright, so now we're standing in the test section. To give you a sense of scale, I'm about 5'11", so this is around 6 feet, maybe just a little bit more higher. And it's a square test section on either side. So what's really cool about having a test section this big is we can bring in full-scale or close to full-scale models, particularly for our industry partners. And we have put all kinds of stuff in this test section. Airplane wings, landing gear, submarine models, and even a couple of times we've had people come in and stand in here to test out hurricane winds for the Weather Channel. My research focuses on the boundary layers that go on the wall. And as you can see, we've got these walls are made out of individual panels. And that's a really cool design feature we've put into this tunnel so that you can swap things out. And the instrumentation capabilities we have here are really remarkable. So now we've taken you back to the drive fan for the wind tunnel. The blades themselves are down right now for repair, but this gives you a real sense of the scale of the facility. The fan behind me is about 15 feet in diameter. One of the really cool things about this facility is that it offers both graduate students as well as some of our undergraduate students the opportunity to come in and do real hands-on research in a world-class aerodynamic facility. Right now we have 4 projects going on inside the wind tunnel that represent 7 graduate students and 2 postdocs who are in here regularly. In addition to that, every year we have around 400 undergraduate students come through the tunnel as part of their undergraduate lab experience. And we're always taking on new projects both inside and out of the aerospace engineering department. With that, I want to thank you again for coming to see this facility wind tunnel with you. If you have any more questions about this facility, please see the website.
What I'm going to do now is kind of build up on this video and provide you further information about the facility and the information. So I'll talk about that. There's a question in the chat about what year students have access to the wind tunnel. It depends on your major. So we host the junior labs. Actually, the junior students are at this very moment using the facility. We also the senior for the aerospace department, and then we host the mechanical engineering labs every year. So altogether, you'll see it's more than 600 students that come through the facility, 600 undergraduate students and grad students on top of that. So what I figured I would do is based on that, just give you a little more information, a little more in depth than what this video actually showed. And first is to provide some information about the tunnel itself. So this is the video. In case you want to find it, you can go to YouTube and look for the Virgin Tech Sibley Wind Tunnel Tour, and it should come up at the very top of the results. So the facility itself is a pretty, like I said before, pretty large scale facility. The test section is 1.8 meters by 1.8 meters and 7.3 meters long. So this is in imperial. This is 6 foot by 6 foot by 24 feet. So it's sizable. Speeds up to 85 meters per second. So that's about 180 miles an hour if you want to convert. And the great feature is that the turbulence intensity, which means the amount of velocity fluctuations around the mean value of the flow, are very low. So you have very clean flow in this facility, and you see it's on the order of 0.07%. In terms of scale, so the test section that I was mentioning earlier, that's 1.8 by 1.8 meter. Highlight this. The test section down here is 1.8 by 1.8 meters. So you can see that in the overall scale of the entire facility, that's the smallest part of the tunnel. So in wind tunnels, your purpose is to generate a controlled environment where you have very good quality flow, very constant speed. So they can then actually test your car or your bike or your airplane or your missile or your rocket or your submarine or your ship or whatever else you got, your trash can, your street lights, to do that in a controlled environment. And for what's called subsonic wind tunnels, so wind tunnels that will be running below the speed of sound, to be able to do that, you're going to contract the flow. So you're going to make the area when you want the highest speed to have the smaller area. So in our case, this is this section down here. So to give you a sense of scale, these guys over here are about 18 feet by 18 feet wide, right? So that's pretty large. Altogether, we're looking at about 20 meters by 40 meters. So for you Imperials out there, it's about 60 feet by 120 feet roughly in overall footprint. So that's sizable. The very nice thing about the facility that kind of what I alluded to in the video is that there's two different configurations we can run it, two different test sections. So the first one is what you would typically expect of a wind tunnel, which is just a simple hard wall configuration, so a duct, a big duct through which you're pushing the flow. And so that's what the vast majority of wind tunnels are. And the way we actually replace the test sections is we have these big hoists and we have air bearings, which are essentially like little hovercraft that allow us to lift very heavy things very easily. And we hoist the test section down, we slide it out into the room adjacent to the wind tunnel, and then we bring the next test section in and put it in position. And that second test section is what's called the hybrid anechoic wind tunnel, or the Kevlar anechoic wind tunnel. So the purpose of that facility is to focus on noise and on acoustic measurements. So you can figure out how loud and where the noise is coming from on a vehicle. And I'll talk about that in more detail when I look at the instrumentation that is used in the facility. But the concept of the entire thing is to essentially try to minimize the reflection of the sound inside the test section. So if you are using the typical test section at the top here, the hardware one, right? These are, this specific case, aluminum panels, half-inch thick. And so if you generate any sound inside of that, just like you're in a room or in any kind of hard wall situation, the sound is going to bounce off the walls, right? And if you're trying to measure the sound coming from your vehicle, you're going to get the sound coming from the vehicle, and then you're going to get all the reflections coming into your microphone system. And so unless the sound, the vehicle itself is very loud, it's going to be very difficult to separate what is sound and what is reflections. So the concept of the hybrid anechoic wind tunnel is to allow the sound to be trapped and prevent it from being reflected. And so to do that, we put these large Kevlar windows. So the yellow walls here is the same raw Kevlar fabric used to make bulletproof jackets or helmets or sails or anything like that. You stretch it on a big frame, you bolt that to the side of the tunnel, and then the sound can escape through that because it's a very thin fabric, but very strong. And then you put some big empty chamber on either side to capture the sound and make sure it doesn't bounce back. And now you can get a very clean measurement, acoustic measurement of your vehicle. But again, I'll go into more details on that shortly. And so that concept, like I said, was developed at Virginia Tech back in 2005, actually. It became operational in 2006, led by Dr. Davenport, or William Davenport, who is the director of the facility, and Dr. Ricardo Burdisso for the mechanical engineering department that helped creating this concept. So what I'm going to do now is show you different things that we've done in the recent past, some as recent as a few weeks back, starting with the fan. So I mentioned earlier that my background is actually a picture of the fan itself. And we've just upgraded that very recently. It came back online less than 3 weeks ago. And so this is the old fan, so the old fan blades, I should say. So the fan is made of 8 blades. They are actually wooden blades made of spruce and covered, in this particular case, in fiberglass. They're powered by a DC electric motor, so 600 horsepower DC motor. So a decent sized car is, let's say 200 horsepower, right? This is 600 horsepower, so it's sizable. And like I said, it's a DC motor, so it's electric. And at full speed, the blades are rotating at about 600 revolutions per minute, so 600 RPM. And we're pulling close to 700 or 800 amps, right? So if you know a bit about electricity, 1 amp can be lethal. 600 or 700 amps, it's like vaporizing type of power. In terms of dimension, that was mentioned in the video, the propeller is 15 feet in diameter. So if you've looked around campus and you know your Pokebird, apparently officially on average, it's 5'10". And so that corresponds to about 2.5 Pucky birds in terms of overall height. It's always difficult to get a sense of scale from this picture, but you saw in the video that it's a sizable thing. And so what we did was we wanted to replace the blade because they were getting old. And so we took the nose cone off. Then we took most of the blade out. So this is the last two blades that were on the fan. Then we were left for a long time with nothing. So the tunnel was down for a long time while the new blades were being manufactured. And we finally got the new blades about probably about 4 weeks ago. And these are it. So these are, again, same thing, spruce blades that are now covered in carbon fiber that have several regions of reinforcement, and then painted in polyurethane paint for durability. And so we went the backward route, right? We reinstalled the blades. So this is with 6 of the blades installed, then the 7th and 8th blade installed, and then the nose cone, which is complete. And so now you have a 1-to-1 comparison on the left, the old blades, and on the right, the new blades, which look pretty cool. They look even better up close because you can actually see the carbon fiber finish on them, which is really nice. And the idea is to make sure that these are more or less bulletproof, so we don't have to worry about damages and cracks and things like that in the future. So how does the facility operate? Essentially, we have activity that's broken down between industrial, so test for commercial companies, test for academic research programs, so programs that are led by faculty within Virginia Tech. Then some educational entries, so we mentioned about that before, undergraduate students and undergraduate student teams, and then some small businesses, especially from right around Blacksburg itself. So to give you a sense of how this actually breaks down, and on the industrial side, we do a lot of work with wind turbine manufacturers. They're very interested in our facility from the acoustic side, the air acoustic side of things, because we're able to actually get extremely good aerodynamic and extremely good acoustics at the same time. And that, with our capability, we're just about at the full-scale condition of wind turbines, so that makes it very important to them, because then you don't have to adjust your data very much to go from the tunnel to the field, essentially. Then, like I said, we have some academic research. So this is research projects that are usually involving graduate students and that are led by faculty within the College of Engineering, primarily, really, mechanical engineering and aerospace engineering. And we have a series of projects right now that are run for NASA. And we have a couple of projects that are run, that are sponsored, I should say, by the Office of Naval Research, or ONR. That are in the tunnel. Then, as I mentioned, we have some small businesses. So 2 examples here, AVEC Incorporated and Techsburg, which are 2 companies that are based in Blacksburg in the corporate research center. And they come here at least once a year, and for 10 or 12 years pretty consistently to do some tests on small business initiatives, usually related to either small-scale transportation or UAVs and drones, things of that nature. And then the last one, which is not the smallest bit, it's probably about 20% or so of what we do, is undergraduate students. So maybe you in the future, who knows? And as I mentioned before, we host the junior labs, like right now, in the facility. We also host some tests for the senior design teams. And we also host the ME Junior Lab, except for this year because of COVID. But and overall, like I said, it's 600 to 800 students that would come through the facility on average every year. So it's sizable, and it's very unusual for a facility that's so extensively used commercially and of this particular scale to be able to be accessible to undergraduate students. And we're very proud that we managed to do that in part thanks to the support of the college to help us doing that. So what I'm going to do next is provide you some sense of exactly what we test, right? There was 2 or 3 quick snapshots in the video of that, but I wanted to show you to have a better idea of what we do. And as I mentioned before, a big chunk of what we're testing are these wind turbine for the wind turbine manufacturers. And so what they're interested in is that if you look at the shape of a wind turbine blade, it's if you've seen one either in pictures or in real life, it's very twisted. The shape itself, the cross section, changes a lot from the root, which start as essentially a circle, to the very end, which is very airfoil looking like. And to design these blades, what the manufacturers do is they take a series of what's called seed profiles. So these seed profiles are like, I don't know, maybe a dozen across the entire length of the blade. And then between these profiles, the shape is lofted in 3 dimensions to get the rest of the surface. And so to get the 3-dimensional full-scale performance, what they do is they base it on the 2-dimensional performance of each of these seed profiles. And this is what we do in the facility. We do the 2-dimensional testing of these seed profiles or the wind turbine sections. And so what you do is you take a 2-dimensional profile, you extrude it over 6 feet, so that's the full size of the test section. And then typically the chord of the model is anywhere between 2 and 3 feet, so 0.6 to 0.9 meters. And so as you can see, we test a variety of different shapes. We're able to test in both test sections. So I mentioned we have a hard wall and the anechoic, so we can mount the models in both configuration if there's a need to do that. And on the aero side, what we would do is we would extract the aerodynamic performance. So essentially, how much lift does the section generate? Because the lift is going to be directly related to how much electricity you can produce. But the second part that's very interesting for the manufacturers is how much noise they generate, because to minimize the cost of logistics and grid integration, you want to get these turbines as close as possible to populated areas. And if they're loud, people will complain. And either you will not be able to build these wind farms, or you're going to have to what's called deregulate them, which means you're going to have to make the turbine run at lower speed to be able to stay within the noise limit. And obviously, you don't want to do that because less speed means less electricity. So these manufacturers come to us to be able to say, okay, well, this particular airfoil is going to make that much noise over that particular frequency range. And so to do that, we use that hybrid anechoic wind tunnel configuration that I mentioned earlier. And this is another view of it to give you a sense of what it looks like. This here is now the Kevlar window, but we're on the outside compared to where we were on the first picture. And you can see that on either side of the test section, we have these big empty rooms, essentially, that are aligned with acoustic foam wedges. So you can see them on this sidewall and the ceiling up here. And the idea is that the sound that will go through the Kevlar will go between the two of the wedges and bounce off several times until it dissipates and does not reflect, right? And so now whatever is generated inside the test section goes out to the Kevlar, gets trapped by the wedges, and does not come back. So if you put now a microphone system, like shown on the right-hand side here, you're going to get a very nice and clean measurement of your sound without worrying about any reflections, right? So that's the power of this particular configuration. And to be able to do these measurements, you're going to use what's called an acoustic phased array, or a acoustic camera, depending on who you talk to. And the way this works essentially is just a large number of microphones. So the one on the right here is our quote-unquote smaller array, which is a 3-foot or 4-foot diameter disc that is instrumented with 117 microphones. And on the left is our bigger array, which actually spans the entire width and height of the Kevlar. So that's physically as big as we can get it. And that's made up of 251 microphones. So each one of these little stud here that you see at this junction of the lattice work is a microphone. So the way this works is that each microphone has been very finely calibrated. So when you generate noise inside the test section, just the fact that, two microphones are slightly different distances to the noise source, the noise is going to reach them at slightly different times. And you can measure that time delay very accurately. And from the time delay, you can actually back out where the noise is coming from and how loud it is. And you can generate an image, so a picture, hence the acoustic camera bit, that shows you the distribution of sound as a function of frequency. So this is what a typical picture would look like for this particular test. That was a idealized like high lift device, and you can see that you see the noise here coming from the corner of the flat, essentially, very clearly. We've also done some tests for landing gears. So on the left, this is an actual picture of the landing gear in the wind tunnel. And then on the right, it's one of these acoustic pictures. And you can see that some of the noise is coming from the gap between the two strut, and then some of the noise is coming from the cavity up above the landing gear. And then when we do tests for the wind turbine manufacturers, what they're interested in is trailing edge noise. So that's essentially as the turbulence goes over the airfoil and gets to the trailing edge, the sound just starts scattering and is being produced right there at the trailing edge. And we can very clearly see here that bar here is the trailing edge of the airfoil with the flow going from left to right. And you can really see how loud it is, and you can get one of these plots as a function of frequency, so you can then figure out how distributed the noise is, or how concentrated maybe the noise is. So this is what we do on the acoustic side. We also have a lot of different flow diagnostics possibilities. This is the first slide on this topic, the first one being flow visualization. So working with air, unless you inject something or you do something to the model, you will not be able to see what happens to the flow as it goes over the model. So you need to introduce something in the wind tunnel to be able to see what's happening. One such option is called a fluorescent oil flow visualization. So you paint the model with a mix of fluorescent dye, and in this particular case, it was just straight motor oil. And you turn the flow on and you put some UV lights on it, and that fluorescent dye will now pop and be very, very bright. And now you can see what's happening. So in this particular case, this is a test that we did for NASA probably 5 or 6 years ago now. And what they were interested in is actually this tiny region back here, where you have some separation at the junction between the airfoil and the fuselage. And they were trying to figure out how to tweak their computational CFD model, so computational fluid dynamics model, to better predict how this flow separates. A very similar method consists in using titanium dioxide. So instead of painting with fluorescent oil, you put a mix of a white dye, a white powder essentially, which is a titanium dioxide, and some oil, and you paint that over the model. You turn the tunnel on, and in this case, what you could see is the flow separation. You can see how you have some region of recirculation here at the top, and you have another region of recirculation here at the bottom. So it allows you to really pinpoint what's happening on the model. We also have a couple of infrared cameras. And the very cool thing about this is that the infrared allows you to see the pressure distribution on the model, and the temperature distribution on the model. And the temperature is going to be a function of how much heat transfer is going on between the model and the fluid. And as it so happened, when the flow goes from laminar, so nice, clean, and organized, to turbulent, that heat transfer changes. And if the heat transfer changes, the temperature signature of the model will change. And so what you're seeing here at the bottom is an image of an airfoil in the wind tunnel. The flow is left to right. And so you can see that that lighter region is the region of laminar flow. And then the darker region is the region of turbulent flow. And everything actually shows up very nicely and very efficiently. And another thing that is a little more common to visualize the flow is to put what's called tufts on the model. And the tufts are just like a small piece of yarn or string or something that you put on the model that will align with the flow when the flow is attached and organized, and will vibrate wildly when it's not. And so the way we have our system set up is we have a series of little tufts here that are made of, it's the material used to make flies for fly fishing. So it's a very thin wire. And so that means the very thin will be able to disrupt the flow as little as possible, even though it will disrupt the flow to some extent. But these are also fluorescent. So you put them under UV light and it just becomes super bright. And so this is a picture of one such test that we did here. And what we have is we have 8 computer controlled cameras, so we can see the model from both sides pretty much at any angle. And this is the kind of picture that you get from that system. And you see that in this particular case, you have some glare, some reflection from the UV lights, you have these markers and so on, but you can actually feed that through a data acquisition, image processing software, and we use primarily MATLAB for this particular purpose. But you can remove all the glare, you can remove everything except for the tuff themselves, and you're left with this kind of picture. And so you can see where the flow is nice and behaved. You have all the tuff that are essentially straight. And when you start getting some separation, you start getting some time averaging, so to speak, right? So the tufts are moving like crazy, so they start covering a much bigger area, and you can actually extract programmatically where the separation line is occurring. So it's a very nice and very efficient program and system. In terms of testing, we do also a lot of tests with propellers for various applications, some general aviation, these guys at the top here are actually marine propellers. In the bottom left here, this is like a UAV, so a ducted fan type of a vertical takeoff and landing option. And on the right, it's a project for the Navy, looking at how this little propeller here, that's on the back of this, bomb-looking body of revolution, how that is ingesting turbulence and how this turbulence is actually impacting both the aerodynamic performance and the acoustic signature of these propellers. So we do a fair amount of tests in that area. We also use lasers a lot, not just because they look cool, even though they look pretty cool, but also because they provide a lot of great information. So you can see it from the picture on the left here and the picture in the top, that what's happening is you can start seeing the flow field generated around these models by injecting something into the flow. Typically, it's kind of like fog that you get from like a fog machine or things of that nature. And you put that into the flow, and you can take pictures of the flow. And from these pictures, you can extract a lot of information about the fluid. So we do that on a pretty regular basis. And one application that we've discovered recently is going to be shown here on the right. And I just want to warn everyone, is going to be some bright flashing lights. So if you're sensitive to that, just look away for a few seconds. But this is a system where we're trying to find the response of our facility to very precise noise source. And the best way we found to do this was to shoot a laser, have it focused right there in the middle of the test section. And what's going to happen is if you focus that laser on a very small area, since it's a pretty powerful laser, it's going to heat up that little volume of air to the point where it's going to create a little spark, right? And that spark is beautifully uniform and omnidirectional. And so you can get a very good response of your facility to this particular noise source. And then I mentioned before, we have undergraduate labs coming through, but we also have undergraduate student teams. So in the bottom left, this is a test we did for the Formula SA team, was it 3 years ago now? In the top, the VT wind turbine team, this is their very first test in 2017, but we've tested for them pretty much every year since then. And then at the bottom, it's a picture of the award-winning, I should say, Hyperloop team from 2017, where they tested the aerodynamics of the shell for the pod that I think it got third place, right, in the competition. So again, we're a very busy facility. So to give you a sense of how much, like we're booked now almost solidly through December, right? And so on average, we tend to be booked about 6 months ahead. So on a pretty consistent basis. So we try to fit students as much as possible when we can. It's not always possible, but like I said, we always fit the labs and we try to fit the student teams as often as we can. And then, as was alluded in the video, we also do some human testing. Not that we really like to do that, but every so often we do get some requests. So on the left, you have Jim the Talent Cantore from the Weather Channel. We call him the Talent because that's how his production team was calling him when we were coming to film. And on the right, it's Randy Case from CNN in 2017. And I would like to point out that I took the two snapshots of the videos at roughly the same speed. And so you can see how Randy has really held it well, while Jim, the talent cantor, was really selling the dramatic impact of wind on himself. And so the reason why they come in here is for them to experience hurricane winds. So that's typically during hurricane season. And so as you can see, they have a full body straps, have these bright yellow straps on them, a full body harness, sorry. And then they're attached to the wind tunnel walls with these steel cables, so at all four corners. So we know they cannot, start bouncing around when things get dicey. It's always funny and nerve-wracking to have them come over because obviously you have somebody in test section, and it's much safer to test like an aluminum model than it is to test a human being. So with that, that will be the end of the presentation / video part of it. This, I will just like to point out this drawing here that was just generated, like, you can see like a few days ago by Stephen White. Every so often in the Virginia Tech Daily News that we receive in our mailbox, there's like this little doodles at the end of the email, and Stephen White contacted us, I think 2 or 3 weeks ago, about coming and drawing something of the facility. And so you have two different scenes here. On the left, it's actually two of our grad students that are currently, as it happens, in the wind tunnel running a test with the undergraduates in front of the fan. And on the right, it's while we were setting up for the test, the wind tunnel engineer and one guy from our machine shop setting up the wall for this particular test. So with that, I'll open the floor for questions. Okay, so we have a question. Do the material used to measure data and so on provide accurate results? And would the material themselves bias the data? So yes and yes. So when it comes to the oil or the paint-based material, or techniques, as long as you paint a very small amount on the model, the impact is minimum. So you can get very good accurate data with minimum impact on the flow itself. But if you're not careful and you apply too much, the paint will accumulate somewhere, and that all of a sudden create a disruption that is influencing the results. The tufts that I was mentioning earlier, these are typically the ones that provide the biggest disruption to the flow. So that's why in our case, since we wanted to be able to get the entire span and the entire cord covered in tufts, we tried to find the smallest material we could to make that work. And so we got something that's extremely thin, so it's really like fishing line, right? So like it's super thin. But the fact that it's fluorescent makes it very bright, and so you can very clearly see it, even though it's a very small thing. So, but yes, you do have to be careful not to disrupt the flow when you use these methods.
Hello?
Yeah, go for it, Lucas.
Oh, okay. All right. Just for the fog simulation, I guess since fog is in air, does the viscosity of fog in any way, I don't know how major it is, but can it affect the flow because the viscosity of it is different than that of air?
Yeah. So when we're using the laser, you mean?
Yeah, because when the intermolecular, because the fog is just water vapor, right, or whatever it is.
Yeah. So typically what we use is actually it's kind of like a purified mineral oil because it doesn't leave much residue, and it kind of just evaporates on its own. And so you have to be careful with the material it's using for that, because one is you want to make sure that when it vaporizes, the particles that are created are small enough that they will move with the flow, and they will not just be too buoyant and either drop or be affected by gravity. So you have to be careful about the amount of seating material you use, the type of materials that you use, and then the particle size that's being generated. So it's something that's actually measured prior to the test to make sure that everything will work out.
Okay, thank you.
Yep. There's another question about what kind of project research do they do for freshman student that would be assigned using the wind tunnel. So for freshman student, we typically rarely have freshmen going through the facility, just because you still have to build your engineering knowledge and so on. We do have some sophomores every once in a while that come and help with research projects, either in terms of setting up the project itself or help setting up the entry ahead of time. And the best way to do that is, if you're really interested in wind tunnel testing and coming to the facility, is to either ping myself or contact Dr. Davenport, who's the facility director, and offer your services as a research assistant, essentially, either for credit or for volunteer work, and go through that. As I mentioned later on, if you're in aerospace or ME, you will go through the facility either as a junior, as a senior, no matter what you do. So,
yeah, I just have one more. So,
go for it.
I heard. So, earlier in the presentation, you said that most things are booked in advance. And okay, say a student wants to use the stability wind tunnel in undergraduate, and it's not for one of these like the F1 team. Would this have to be? Does that ever happen? That's my question.
So no, typically it would have to be either part of the student team or a research project that's backed up with a faculty, or like a senior design project. That's typically the three kind of configuration where we're able to offer time for the undergrads.
Okay, so otherwise it's not an option, I guess.
Correct. Yeah,
okay.
It's just too busy, so we have to be able to make that work.
Thank you.
Okay. There's one last question about being able to see this during the campus tours. Unfortunately, no, partly because we're so busy. It's not going to be possible to come and physically see the facility because it's running so often. The question is, do people come to the wind tunnels just to watch? We don't have that option. Like I said, the best way to watch a test is to try to get involved as a research assistant. So to be able to come and see how things work. You can find my information on the AOE website. You can look for the Stability Wind Tunnel website that has a lot of information about the facility itself. And if there is no more questions, I will end it here. Great. Well, so you guys have a good evening. Good luck with your academic careers. And if you go through the aerospace department, I will probably see you in your junior year because I teach the junior lab that's currently ongoing. So hopefully I will see you guys then. So you have a good evening.